Today, we're going to talk about a technique that is, no joke, shaping the world all around us. It's called post-tensioning. And honestly, it's like a hidden superpower for concrete, letting engineers build some truly mind-blowing structures.
All right, let's just jump right in. Think about this for a second. The big challenge for builders today is, well, it's a huge one. How do you build longer bridges, taller skyscrapers with wide-open floors? And how do you do all of that while using less material? It's this constant balancing act, right? A real puzzle of strength versus weight versus cost.
And this is where you can really see the difference. On one side, you've got your traditional concrete. Yeah, it's strong, but it's also thick, heavy. It just kind of sits there passively waiting for a load. But on the other side, that's post-tension concrete. It's way more slender, it's lighter, and it has what's called active strength. What's that mean? It means it's already working, already pushing back before you even put a single pound of weight on it. And that difference? Oh, it's a total game changer for architects. So, here's how we're going to break it all down. First, we'll look at the superpower itself. Then, how it actually works. We'll check out some of the amazing things it can build, touch on the challenges and risks, and wrap up by looking at what's next for concrete.
All right, let's get into it. The structural superpower. You know, we're even having this conversation because regular old concrete, for all its strengths, has a bit of an Achilles heel. It's not great when you try to pull it apart or bend it.
So here's the big idea behind it. Post-tensioning is this really clever way of, well, pre-stressing concrete. Imagine this. You put these super strong steel cables, engineers call them tendons, inside the concrete forms. But here's the key part, the part that makes all the difference. You don't pull them tight until after the concrete has hardened. Once it's strong, you tension them, and that whole process actively squeezes the concrete, putting it into this constant state of compression. Okay, so how exactly do they create this active strength? That's a great question, and it takes us right into our next section, how it works. Let's take a look at what this process actually looks like on a job site. It really boils down to 4 main steps. First, they lay out these flexible pipes or ducts that have the steel tendons already threaded through them. Second, they pour the concrete all around those ducts and just let it cure, let it get really hard. Then comes the cool part. Powerful hydraulic jacks grab the ends of those tendons and stretch them. I mean, really stretch them. And finally, they lock them into place with anchors and usually pump the ducts full of grout to keep that steel safe and sound. Okay, this is the perfect way to understand the core principle. I love this analogy. Just imagine you have a row of books and you want to pick them all up without a shelf. What do? You squeeze the ends together, right? If you squeeze hard enough, you can lift the whole row. That is exactly what post-tensioning does. That constant squeezing force fights against any bending that would normally just crack the concrete.
And we're not talking about a little squeeze here. The forces are just immense. Get this, in one real-world project, a conference hall roof, they stretched those steel strands by 172 millimeters. That's almost 7 inches. Can you imagine? That stretching basically crams a huge amount of stored energy into the concrete, giving it that incredible active strength, like it's always coiled and ready to push back.
So with that kind of power, what can you do? Well, that's what this next section's all about. Building bigger and thinner. Let's look at where this tech is really changing the game. Honestly, once you know about it, you start seeing it everywhere. It's the secret behind those super long, elegant bridge spans that look like they shouldn't be possible. It's what makes soaring high-rises work, with floor slabs that are way thinner and lighter. And you know what that means? Fewer columns. Think about it. Huge, wide-open spaces in offices, parking garages without a forest of pillars. It's all about getting more usable space. Here's a great case study. A huge residential complex in Seoul. What the engineers did there was pretty brilliant. They used post-tension slabs for all the floors, which is pretty standard, but they also used it in the outrigger walls. These are major structural walls. Why? It wasn't just to hold up the building's weight. It was also to fight against the massive sideways forces from wind. It's just a perfect example of a smart, efficient, integrated system. But of course, a system like this is only as good as its parts. The materials really, really matter. There was a recent study in 2024 that dug into this, looking at how well the steel tendons actually bond with the concrete around them. And what they found was pretty clear. The stronger the concrete, the better the bond. When they went from a standard strength concrete to a really high strength mix, the performance just shot up. So the takeaway is simple. You need a seriously strong concrete mix for this whole thing to work the way it's supposed to. Okay, but with great power comes, well,
This kind of technique demands absolute precision. And that brings us to the challenges and risks, because if you want these incredible buildings to last for decades, you have to be obsessed with durability.
And believe me, engineers have a lot on their plates here. Research shows a whole list of things to worry about. First up, corrosion. If any moisture gets to those steel tendons, it's bad news. Then, over time, concrete has this habit of slowly shrinking and, well, creeping, which can cause the tendons to lose a bit of that crucial tension. Add in things like freeze-thaw cycles and it gets even tougher. But the number one thing, the one everyone points to, the quality of the installation. It has to be perfect.
And this is a perfect, if a little scary, example of what happens when things aren't perfect. This quote comes from that same conference hall roof study. Investigators found that the anchorages, the hardware holding everything tight, had actually warped, and the steel strands themselves had moved. It's just, wow, a stark reminder that in a system like this, there's very little room for error.
So with all that in mind, where are we headed? Let's look to the horizon in our final section, the future of concrete. Because what we're seeing is a shift. We're going from just a strong material to a genuinely smart system.
Post-tensioning isn't the final chapter, but it's a hugely important one. Think about the journey here. We started with the Romans and their incredibly durable concrete. Then, boom, the 1800s give us reinforced concrete with rebar. Fast forward to the mid-1900s, and post-tensioning becomes a commercial reality. Each one of those steps was a massive leap forward. And the next leap? We're living in it right now. It's all about making these systems smart and sustainable.
And the stuff coming down the pipeline is just so cool. We're seeing researchers mix post-tensioning with new wonder materials like ultra-high-performance concrete to get even more strength. They're putting tiny sensors inside the concrete to monitor the building's health 24/7. They're using super powerful software to figure out the absolute perfect layout for every single tendon. And on top of all that, they're finding ways to do it all with greener, low-carbon materials. It's really the best of all worlds.
So it really leaves us with this final thought, right? Post-tensioning gave us concrete that's actively strong. It's not passive anymore. And now this next wave of tech is making it smart. So you have to wonder, what does that unlock for us? When our building material isn't just strong, but it's also smart, what are we going to build then?